My name is Olle. This is going to be an educational talk. It's not going to be much in terms of new research or anything, but I thought I'd do a kind of a summary of this area about DOMXSS, just because it's something that I've been playing around with in like weekends at the end of last year, actually. So it's like kind of a hobby project for me to learn more about it, and then I thought, why not speak about it and teach you guys what I learned. So yeah, let's get into it. So when I think about DOMXSS, I immediately, let's see if I can switch slides. Why can't I switch slides? Jesper, it's your fault. You said I should use kiosk mode. Okay, so we're not using kiosk mode, we're using windowed. Sorry about that, I'm professional. So when I think about DOMXSS, I immediately think of this guy, Stefano De Paola, because he's the guy who really kind of brought it to my attention and did a lot of research and was teaching people about DOMXSS quite a long while ago. I think a lot of his work was back in 2010 to 2012 timeframe. But he's kind of Mr. DOMXSS in my mind. So that's one of the many resources, one of the biggest resources that I used when researching DOMXSS is his old writings and blog posts and stuff. And he's still active today. So what is DOMXSS? Well, in your traditional reflective XSS kind of thing, your attack scenario is that the attacker sends some kind of a phishing link or something like that. Basically a rigged URL with some malicious payload. The victim then visits that URL, goes to the server interprets it, and responds back to the client with some kind of script injected into the wrong place, right? That's kind of your classic definition of reflected XSS. So what is DOMXSS? Well, I like to think of DOMXSS as like client-side XSS. So you're basically cutting out the server from the equation. So the attack scenario is that an attacker would prepare a link with some malicious payload, would send it to, or somehow get the victim to visit that link, and then the actual evaluation of that payload happens entirely within the browser. Right? So it doesn't depend on server-side components triggering the payload and injecting the scripting into the markup. It's done entirely within the JavaScript engine of the browser. So that's kind of my definition, at least. I don't know if it matches everybody else's definition, but that's kind of my definition of DOMXSS. And I personally would have liked to call it like client-side XSS or something like that. But now that term is out there, DOMXSS is kind of stuck as the term for this. So, okay, what does it look like? So this is client-side JavaScript that's vulnerable to this kind of problem. And exactly what is happening, I'm going to walk you through it like step by step. So the first line of JavaScript here, oops, why is this not working? What? Now I can't blame Jesper, now it's my fault. Why are my animations not working? Okay, so I deleted my nice animations that I was going to show you, so, okay, sorry, this is embarrassing. I can do better than this. Okay, I'll have to point using my finger and hope that people on the stream can kind of see it. So I had nice arrows pointing at the code. So the first line here takes something out of location.hash, which is an object in JavaScript that contains the URL. The location object contains the URL, and the .hash property there contains what is after the hash mark in the URL parameters. So first of all, you have your host name, and then you have your path, and then you have a question mark, and then you have some parameters, and then after that you can have a hash mark, and then you can have other stuff. That other stuff is really meant for in-page navigation, so it's usually called a fragment. And in the original usage, it matches up with an anchor tag so that you can click on a link and be sent to like auto-scrolled to a different part of the same page. That's kind of what it used to be used for. Nowadays, it's used for like single-page web apps, JavaScript client-side frameworks to do in-page navigation in other ways. So a very common thing is that you see JavaScript code looking at location.hash and the contents of that, and then acting upon whatever data is in there. So it kind of stores its own data in the URL that way. Then it's putting that data, so whatever's after the hash mark in the URL, it's going to be our payload when we're exploiting this, puts it into a JavaScript variable. This variable is called page in this example. And then it looks up a div tag, just finds a tag in the HTML markup, and it uses the inner HTML property of the div tag object to inject some HTML into the page, right? And there's your injection. We have the tainted page string that's being concatenated with some HTML markup, and then it's going to be inserted into the DOM, the document object model, the in-memory JavaScript representation of the web page that the JavaScript uses to change what's shown on the screen or change the markup of the page. So what we're looking for in like a DOMXSS scenario is somewhere where we have user input or attacker controllable input, usually in the form of part of the URL, right? Because that's something you can construct a malicious URL and send to somebody in your attack scenario. And then you need to kind of follow that data through to, and that point where you are able to inject data is usually called a source. And then you follow the data flow through the scripting to something like div.innerHTML, which is called a sink, and that's where your data that you can control is injected into the DOM. And that data flow is very simple to follow when it's just 3 lines of code. When it's 3 layers of client-side JavaScript frameworks in between the source and the sink, that data path becomes very, very tricky to follow. So. But that's the pattern that we're looking for in DOMXSS, is that somehow we get attacker-controlled data that then ends up in an unsafe way being inserted into the markup of the page or the DOM. So DOMXSS is kind of a problem. It's a painful problem for people. Google said in their, this is statistics from Google from their bug bounty program or EVP program or whatever they call it from a couple of years back, where they say that researchers contacting them about bugs in Google products, it's mainly XSS stuff that they have to fix. So even Google, who you would think would have a good handle on web security in their products, still has a huge problem with XSS. And last year, even Krzysztof Kotowicz from Google said that right now, DOMXSS is the most common type of XSS at Google that they encounter in their own code, in their own products. And he gives some reasons, like I mentioned, growing complexity of the client-side code. So we have huge stacks of JavaScript frameworks on top of JavaScript frameworks running in the browser today to build these modern, fancy UIs and websites. And he also said it's hard to prevent and it's hard to detect. So why is it hard to detect? Is it really that hard to detect? This is some other interesting, well, it's actually the only published statistics around DOMXSS that I could find in 5 minutes of Googling. It's from a company called NetSparker that they make web scanning technology. So they published last year some statistics about what kind of vulnerabilities they find with their product, or their users find with their product. And they said that out of the XSS issues, like 4,000 XSS issues, only 40,000 XSS issues, only 1,200 were DOMXSS. Is that really true? When Google says it's the main problem, or it's the largest type of XSS that they have problems with, NetSparker on the detection side says that it's a small part of what they see. Maybe it's because it's a bit hard to detect using these kind of tools, right? So maybe it's not that it's not prevalent, maybe it goes undetected because it's hard to detect using these tools. Why is it hard to detect using these tools, like web scanner technology? Oh, here are my nice... Sorry, I should have prepared better. Apparently, I duplicated this slide, but not the animation. So here are my nice animations. So we have your source of attacker-controlled data, and the URL fragment after the hash mark was what I talked about. So that's what location.hash contains. That gets put into a JavaScript variable. The JavaScript variable then ends up in one of these sinks. And there are many types of sink. It doesn't have to be inner HTML. It can be different, like the classic is document.write that actually puts HTML markup directly into the page. There are many of those types of sink. And the trick to finding DOMXSS is identifying both all of the possible sources of attacker-controlled data and all of the possible DOMXSS sinks, and then tracing out all of the data flows from all of the sources and seeing if they end up in one of those sinks. And then when you've done that, then you probably also, to weed out false positives, need to figure out, is there any kind of filtering or escaping going on during that data path? Because you can't just assume that data flows from source to sink, and that's a problem, because it could be made safe. The data could be made safe during that time, right? So it is a pretty tricky problem to identify, and it's a pretty tricky problem to identify in the way that web scanning technology likes to identify problems, which is with a high rate of true positives and a low rate of false positives. They don't care too much about false negatives, but false positives is a huge problem when you have developers, for example, running web scanning technology. That really is a problem for them. If they get a huge amount of false positives, they think they just can't use the technology because it's wasting their time if they have to investigate all these false positives manually. So back to Stefano De Paola. He actually has a nice wiki page. It's migrated onto GitHub, where he lists all of his research into what are these sources and sinks that can give rise to DOMXSS problems. So that's a really good way of learning more about what these sources and sinks could be. So I really recommend that. There are also loads of great tutorial sites out there that can help you play with DOMXSS. So DOMXSS.com, for example, is one. Google has an XSS game.appspot.com that I think contains some good examples as well, but it's structured more like a war game type thing. The one I really like is DOMGoat, domgo.at, which looks like this and is really, really built for people to quickly be able to understand and play with client-side XSS or DOMXSS problems, and to really understand the relationship with the vulnerable code patterns and this data flow that I talked about. So that's a really good site if you want to play around with DOMXSS and learn more about it by practically trying it out yourself. So I'm going to go into a bit more about why it's hard to find DOMXSS and the methods that are used to build tools to identify DOMXSS problems. And after this, you'll have a better understanding of exactly why it's tricky to identify these problems using tooling. By the way, it's super tricky to identify these types of problems without tools as well. It's practically impossible using no tools, because then you have thousands of lines of JavaScript code and all of these interacting frameworks, and following code paths manually and reading line by line just does not work for identifying DOMXSS issues. So you need some good tooling to help you find them, and that's tricky. So I'm going to explain why. So it's all about taint analysis. Taint analysis is a studied problem in computer science. It's a method to, let's say, mark a piece of data and be able to follow that piece of data as it moves around the program, as it's passed between functions and between different parts of a piece of software. So you mark this data as tainted at the source where you want to follow it from. So, for example, one of these DOMXSS sources. And you have to mark it in such a way that you're able to follow the propagation of this data. So if the data gets put into like a string function and then they're transformed into a different string that follows out, you still want to be able to follow that this data is still possibly tainted. So it's not following one variable, it's following the contents of that variable as it gets passed around and put into different variables and perhaps transformed using other functions and string, substring functions and things like that. You still want to follow those parts of the data that came from your marked source as tainted. And this is super hard to do if you don't have proper tooling to do this built into the language, for example. You can do it in some languages that have strong typing. You can do this with types. In other languages where you don't have that, you have to have it built into the language tools like a compiler or interpreter. So you follow the data as it's passed around in the software. As I said, when it gets propagated between functions, you keep that taint on the data. Even though it's in a new variable, in a new part of the code, you can still follow the contents of the data. And then you alert if this tainted data somewhere is passed to one of these sinks. So a dangerous function that inserts HTML code into the page, for example. So that's the idea of taint analysis. And taint analysis can be performed practically in two different approaches. So you can do it in the static approach or the dynamic approach, and I'll go into those separately in more detail. So the static approach, which is the one that's a bit easier to implement perhaps, and that's used by these tools, if you recognize those. Often the most simple way to do the static approach to taint analysis is just grepping for these sinks and then, letting the user do most of the work. So getting you maybe 20% of the way using the tooling, and then you'll have to investigate the rest yourself, because the whole taint analysis thing is kind of tricky to do. Why is it tricky to do? Because of these large frameworks and complex client-side code, they kind of obscure this data flow. It's hard to follow that data around by just looking at the code and understanding what it does. So static analysis tools, they look at the code and then using heuristics and rules try to figure out what the code does. So it's basically automating what you would do in like a manual code review, where a programmer looks at the code with their eyes and try to figure out in their head what the code is going to do. So the tools that use the static approach, they just try to help the code auditor to do manually walk through this code and try to understand it by looking at it. It doesn't work too well in practice, just because of this the complexity of these JavaScript frameworks. It's easy to miss something or misinterpret how the code is going to be executed. One reason is that JavaScript is, and especially JavaScript in the browser, it's a hugely dynamic language where most anything within the DOM and within the language itself can be modified at runtime. So you can't really look at one piece of code in isolation and figure out what this code is going to do when it's run, because it depends on the JavaScript environment and the DOM and the runtime state of the browser, which could have been modified by another piece of code in some other framework, some other place. So you can't just look at one code file or one function and know what it's going to do, because it has so many dependencies on these things that are modifiable. I think this illustrates illustrates the problem quite well. This guy put up a Twitter poll asking, when burp tells you about DOMXSS via static code analysis, how often is that a false positive? And yeah, I think 70% or more in his poll. And I don't know about your experience, but I think that's the common understanding, is that static analysis tools aren't really working that well for this problem. So let's look at the dynamic approach instead. So the dynamic approach, which was pioneered by Stefano De Paola in his tool DOMinator, which is still available if you want to take a look at it. It's up on GitHub. It was turned into a commercial product a couple of years later called DOMinator Pro that he sold through his consulting company. Basically, the idea with dynamic taint analysis is you instrument a real browser JavaScript engine for some value of real. So you take this environment that I talked about, where you have a JavaScript engine, you have a DOM, you have the browser state. And then you put hooks in the code that implements this so that you can follow the tainted data. So you can mark data as tainted and you can follow the data flow and do dynamic taint analysis, which is basically executing the code and seeing what it does. So you don't need to understand what it's going to do if you could have this environment set up which simulates a target browser, and then you can just run the code. And you can see what the outcome is and get a very good understanding of if it's a problem or not. So this means, of course, that you have to make changes to this code. You can't run a real browser unmodified because it just doesn't have this code that tracks tainted data through the data path. So that's something that you have to add. And what Stefano De Paola did with DOMinator was he took Firefox and then he modified the Firefox code to implement this data taint analysis to follow the data flow through the JavaScript execution. And then he could write simple rules for the sources and sinks, and it would automatically alert you when a piece of data that was tainted at a sink, tainted at a source, ended up in one of these sinks. And it would give you nice contextual information and point to exactly where in the JavaScript code this data path, actually all of the steps in the data path could be pointed at which code lines were, so you could follow it in. And it was very good and very high signal output with low false positive and a very good chance of catching actual bugs. So you run the code to see what it does. Seems simple enough, right? Actually, Burp has also implemented this late last year, at least a simple variant of it, where they have a simulation of a browser JavaScript engine that they can run the client code that they see in the browser, in the Burp suite, and actually do this kind of dynamic taint analysis, because they figured that this static approach that we had so far is not working out too well. It needs some improvement. So they're also going this route. DOMinator was replaced recently. DOMinator Pro product was replaced with a company called Blue Closure that sells this kind of technology and some other stuff. So if you're interested in buying tools to do this, then these are the available options that I know of. The problem with the dynamic approach is that browsers change all the time, and the web standards change all the time, and the browsers implement the new web standards, and all of this code in the JavaScript engine on the browsers is changing all the time. So keeping your, for example, DOMinator modified Firefox code up to date with the latest Firefox code base is a constant pain, because it breaks all the time, because they change the Firefox code and then you have to go back and fix your patches to the Firefox code. And Burp is probably going to have either that kind of problem, or they're going to have the problem where they have an implementation of a browser JavaScript engine that's not keeping up with the changes that are happening in the real browsers. So they're getting not a perfect simulation of what a real browser would do when executing the code, which means more false negatives and possibly false positives. So it's a major pain to keep these modifications to an existing browser code base up to date to do dynamic taint analysis. And I think that might be why it's limited to commercial tools. As you can see here, I only know about 2 tools that do this kind of thing properly, and they're both pay tools, right? So we talked about the static analysis techniques that don't work really well. We talked about dynamic approach, which seems to be more promising. But I'd like to present to you today my take on this. There's also a third way. There's the hillbilly approach. So kind of ghettoing it up a bit. We already have a browser. I mean, I have a browser here, look. I have a browser, right? And the browser has a JavaScript engine. And the JavaScript engine allows overriding almost anything in the DOM and in the JavaScript execution state. So it's a very dynamic language. What if we don't go what if we do taint analysis not in the correct way, as I explained earlier? What if we taint the data in line with the actual data? So we take the input and we transform it into input, and then we add some unique string into the actual input at the source. And then we just look at all the sinks, and then we see, does our magic string turn up at one of the sinks? So we don't really care about the data flow. We're just injecting some badness at all the sources, and then looking at all the sinks to see if we see evidence of our badness there. So it's kind of the hillbilly approach to taint analysis is just don't try to follow the data path. We know it's hard. Just inject some crap at the sources and look at the sinks and see what falls out. And the great thing about this is it's 100% doable using in-browser JavaScript. So you don't need to modify your browser. You can run your regular Chrome or Firefox or whatever browser you like, the latest version, and just add some client-side JavaScript that does this instrumentation dynamically in the JavaScript engine. So that's pretty cool. So I tried to hack this up during a couple of weekends last year, and I'm releasing this code. It's already on GitHub. You can have a look at it. I'm really bad at naming, so I call it the taint testing tool. But I'm going to show you how it works. So you can go clone this GitHub repository. And then you take I'm going to show you how to do it with Chrome, but it works pretty much the same in other browsers as well. You just have to find out how to inject client-side code into every web page in Firefox or whatever your browser preference is. So this is packaged up right now as a Chrome extension. And the only thing that the extension does is to inject this client-side JavaScript into every page. So to load it, you have to switch on developer mode. Just because I haven't gotten this approved, it's not on the official Chrome Web Store. It's just a cloned repository, right? So then you click Load Unpacked, and you point it to the directory where you checked out the Git repository, and then it loads the extension for you. Then you want to go into the details view here and change something. So maybe you don't want to run it on every page, because that can be a bit of a pain in the ass, and you might accidentally attack something that you shouldn't attack. So I usually switch it to on-click, which means that I actually have to click this icon up here to get it to run on the page. You can also have a whitelist here. So if you're running Bug Bounty, for example, you can add a whitelist here, and it will automatically run on all those sites and no other sites. But I like the on-click option, so I'm going to use that. So I tried this thing out, and I went to an organization that I think would appreciate a free pen test. And I checked out some stuff that they had there. So they have a property called WIS. Let's see. Oops, I clicked something wrong here. WIS, which is some kind of a web app. And when you clicked on the help thing here, it gave you a help thing. Now it's actually you have to do one more click to find the help thing. So here's the help for the web application. So it's nice menu-driven help system where you can search for stuff and you can get information on how to use this web application. And as you can see up here, it's quite interesting what the fragment looked like. The fragment looks like a path to an HTML file. So I thought, that's interesting. What if I put anything else in there? So put it blah, blah, blah in there. And it says, it can't find the page. Let's find out what it's doing. So if you start developer tools, you look at the network traffic, you reload that, and you see it's trying to fetch documents and blah, 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 right? So whatever I put in the location fragment here, it's going to try to fetch that as a resource, as a web page, and inject it into here. So let's not do it like the hard way. Let's do it the easy way. Let's see if our tool can automatically identify this as a problem. So I'm going to start the tool. It's going to inject a lot of crap in all the sources. So for example, the fragments. And let's see if it works. If it doesn't, it's going to be the third. Why is it not working? Okay, I'm going to reload the page. There we go. So you didn't see it, but there was a notification that popped up, and there's a little badge here saying 1, which tells you if you didn't have the console open that there's a problem identified by the tool. And the problem is that this tainted string ended up in an XML HTTP request, which is one type of sync that you want to have a look at, because it's fetching a resource from a URL that we control. So we can do something to exploit this. Let's see. So if I put something, if I don't put like a relative path in there, instead I put, let's say HTTPS : let's see if this works. Oops. So as you can see, this is one kind of DOMXSS issue, where something we put into the URL in the fragment gets ends up in an HTTP in an XML HTTP request to whatever's in the hash, right? And it fetches that and it inserts it into the DOM. I fetched my own page, which contains some JavaScript, and that JavaScript is inserted into the DOM, and we have code execution. So instead of having to look at the code, I can just go to the page, start the extension, and it identifies the issue for me. And I actually have to go to either, I can show you. The issues also show up here in the background page of my. That's the identified issues list right there. So it tells you on this URL, we found a problem. This is the sync. This is the data. So even if I navigate away from the page, I don't lose the information that I gathered through the extension. It's actually all saved here until I reload the extension or restart the browser. So this is kind of the site that I was playing around with first when I was developing this. And it used to be that let's see. It used to be that the web application, you clicked on this help link here, it would take you to a subdirectory on the same domain, and they had this help thing there, and it was vulnerable. When I reported this to them, they figured that the easiest way to fix this was not to rebuild the whole help site. So they just migrated the help site away from the web application and put it on a separate domain. So it's still vulnerable, but it's on a separate domain, so it can't hurt anybody, right? You can inject script into the help domain all you like, but all you can do is like fiddle with the help contents and nobody cares. So that's how they decided to fix this. But let's look at something else that this organization provides. They have, I'll just go directly to it. They have another, like an informational website. Let's run it on there instead. So unfortunately, I made sure that this bug was fixed before coming to speak at this conference. So I'm going to have to show you some static images of what it looked like instead of actually doing it in the browser. I can do it in the browser afterwards, but this is what it looks like. You load up the site. You activate the extension. The extension identifies some issues, and you look at the issues in the JavaScript console. And you can then have a look at exactly what the code is, where the injection happened, and then you can start to figure out, is this exploitable or not, right? So I can't show it on the actual site, but I can show it on a saved copy of the vulnerable code. So let's run the tool. This is what it looks like. It identified 4 issues. Oops, that's not the right thing to do. Developer tools, console. So it identified a DOMXSS and document write, and document write was called and injected this code. And then we can have a look at, it actually identifies the same issue with several different methods. So the same tainted data is ending up in several of my inspected sources. So it's also finding it in a DOM injection here into child node, for example. So, if we have a look at this, let's see if we can see. No, that's just my code. That's not correct. If we play around with this a bit, I can show you how to exploit it as well. So we had something in the hash, which gave us in this case, a syntax error. So already there we know that we have something that's affecting the JavaScript execution. And we can actually have a look and see, let's see if I click the right thing. That's not the right thing. This is where it's triggering the exception. So I didn't prepare this very well. I have a cheat sheet that I can show you otherwise, but yeah. So I'm just trying to figure out if we're in a document is sandboxed. Let's see if we can look at this. We can. Great. So this time, we didn't get a JavaScript syntax error. I fixed the syntax error, and I'm actually now trying to execute JavaScript. And this time, we can actually get a link here that shows us the source of the JavaScript that's being evaled. And then we can see my injection ended up here. So this is where the injection ends up in this bug. We're creating a JSON object, and this is the URL that's being put into one of the methods of the JSON objects, and they're quoting the strings with single quotes, and they forgot to escape the single quote that appears in the URL. So which means that I can inject stuff into this JSON object. And apparently I couldn't do an alert straight off, so I'm going to go to my cheat sheet. Let's see. I'm just going to grab this. I think this is a good one. And paste the exploit into there. And then I have to restart the web server because I stopped it. And we get script execution. So the trick here was that instead of evaling alert directly, I used the A to B function, which decodes base 64, and then the script that I'm trying to execute is base 64 encoded. So that passes all of the different checks and escaped sequences that are along the data path. So if we, for example, do this to show you what that thing actually was that was executed, it was top.window.alert DOMXSS on document domain. So that's what all this stuff is about. So That's an example of exploiting DOMXSS. Let's get back to the content. So this was in this bug that I just showed you and just showed you how to exploit was in a quite popular social media sharing thingy-majig, which is a third-party service where you link in some JavaScript into your web page and it adds some, share this on Twitter, like this on Facebook, buttons into your web content. And you do that by including this sharethis.com/button/buttons.js file. And that JavaScript somewhere in like the third thing, it loads and executes. It creates an iframe and creates this JSON object. And that's our sink where our code, our injected code ended up. So I had a look at public www. Shout out to Linus for giving me a tip about this great search engine. It allows you to search for the source code of all of the sites that they've crawled on the internet. So it's a great way to find out who's using this particular third-party JavaScript. And it turns out there's quite a lot of web pages that use it, among others, some high-profile brands. So as I said, this particular bug was fixed like yesterday or something. So it's actually not live anymore, but it was a really good example of a DOMXSS bug that was super tricky to find by manual inspection and was hard to find by static analysis because there were so many layers of JavaScript code calling JavaScript code in another JavaScript file in an iframe nested in another iframe. So it was super hard to find with static analysis or code inspection, but our tool just directly could identify that it has a problem. So how do we fix DOMXSS issues then? You could say CSP, Content Security Policy. That's like a more generic way of fixing XSS issues. I don't think that that's a particular good way of fixing DOMXSS. If you want to eradicate DOMXSS as a bug class, it's definitely not the way to go. CSP is pretty hard to retrofit into existing websites for one. So just one thing about this bug that I showed you. I think the reason that bug exists is that they used encode URI to encode this, the URL of the page when they put it into the JSON object. And encode URI doesn't escape single quotes. And they were using single quotes to construct a JSON object. So that's a common mistake that could happen if you try to make data safe by encoding it with encode URI. You might have a bad time. Encode URI is meant to encode data that you're sending over HTTP to the server. It's not meant to make strings safe for JavaScript inclusion in the DOM or something like that. It's just not what it's for. What about escape? You could use escape instead. It does the same thing. It percent encodes special characters. Well, escape is deprecated by the World Wide Web Foundation or Consortium. And the reason for escape, it's a built-in JavaScript thing, and it's meant to be used to escape JavaScript strings. So if you're putting something into a JavaScript string and you don't want it to terminate the string, that's what you're supposed to use it for. So it's not really a great solution otherwise. And I think the real solution to fixing these problems is using something that's context aware. So escaping the data, or making the data safe, I should say, for the particular context where it's being used, which means that it should probably be made safe pretty close to the place where it's used, so close to the sink where it's being added to the DOM, for example, because otherwise you don't know what the context the data is being inserted into is. So if you do it at the input validation stage, if you do it when you take it out of location hash, for example, you don't really know where it's going to end up, so it's hard to make it safe when you don't know the context. So the right way is probably to build this into our client-side JavaScript frameworks that we use to make single-page web apps, modern UI in web apps. And that's pretty hard when you have a lot of legacy code. So it's not going to solve the problem for all those people who have written code in Vue.js a couple of years back and now figure out that they have huge problems because of just this context awareness that I was talking about. So this guy is complaining that Vue.js is double encoding his umlauts. So all of his German characters are not showing up correctly in the web page. And that's because on the server side, somebody has already encoded this data to be inserted into HTML. And then he's using a Vue.js framework that's then percent encoding that again, and it shows up as garbage or emoji bucket. So, and he says, how can I handle this? Can I disable all the escaping and make this even more unsafe? And yeah, so you see, it's going to be a bit of a problem to fix this properly. So I think the right way is moving towards building in protections into our client-side frameworks and then hoping that as people move to more modern client-side frameworks, they will get the benefit of these things. And if you want to know what's being done about DOMXSS problems today, you should follow this guy. Krzysztof Kotowicz of Google is working on a new extension to the web standards called trusted types. And that's exactly what I was talking about earlier. It's injecting into not the language, but into the DOM JavaScript bindings, the framework that we use to Can you hear me now? Good. Okay, so I think the batteries run out. I'm going over my time, that's why. Okay, so Krzysztof Kotowicz has been working with the W3C or the WICG, with some kind of working group. I don't know these things because I'm not really into how the web standards are being developed. But follow these links. The slides are going to be available. You can watch the stream. Follow these links and learn more about the Trusted Types Initiative, which is injecting into these standards a way for you to mark your JavaScript strings as being safe or unsafe. And then you can just, when you're taking strings and putting them into the DOM, for example, at all these syncs, when you're doing inner HTML, for example, then you can make sure that you only take a trusted type string and insert it into the DOM. So you're kind of using trusted types as a way of differentiating from unsafe JavaScript strings, which could contain anything, and trusted type strings, which are safe for use, right? So that's kind of the idea. I haven't had a chance to understand it completely yet, but have a look at it. There's even a jsbin.com link there where you can play around with using trusted types in DOM Purify, which is a really good framework for making stuff safe for inclusion in web markup without having script injection problems. So I've gone over time, but if you do have any questions, we might be able to have a couple of questions. And I have some goodies here, some giveaways for people who ask questions. So you'll get a reward if you ask a question.
Do you want to use this one instead, and I'll run out with that one? Okay, can we see a show of hands? Any questions? Come on, guys. Oh, I see one over here.
Hi.
Hey.
Great speech, by the way, and good demos.
Thank you.
I had a question regarding if you safeguard your environment by setting, for example, security headers. To what extent is your opinion that they safeguard you about considering cross-site scripting and particular DOMXSS?
Yeah, I'm not an expert in this subject at all. And I kind of glossed over the whole CSP thing. There's probably some things that you can do to more generally protect against XSS exploitation, but that's not something that I've investigated more that I'm comfortable talking about, giving advice about. What I do think is that DOMXSS is the one type of XSS where those mitigations are kind of weak, where they don't work very well. So I think the real way of solving the DOMXSS issue is kind of eradicating the whole bug class by making sure that we use JavaScript in a secure way instead. And that can only be done by implementing that in the frameworks that developers use. This can't be something that's left up to the individual developer to understand how to use, how to take data input safely and pass it into the DOM. It has to be made safe by the frameworks. So I think I had so this slide shows an example of that from the React framework. They actually do safe inclusion in the DOM, and if you want to actually include stuff that has the potential to include markup and scripting into the DOM using React, you have to call a special function called dangerously set inner HTML. And that kind of gives a signal to the developer that, oh, maybe I should find out what that dangerously part means. Maybe this is something I should be using carefully. So I think that the only way to solve DOMXSS specifically is that all of these client-side UI frameworks fix the problems for the developers so that they're using safe ways of manipulating the DOM. I hope that answers the question somewhat. Thank you. You'll come collect the prize.
Any other questions? See a hand in the back. All right.
So I might have missed this, but the talk is called DOMXSS is not dead. How long do you think it will take before it's mostly dead?
Well, going back to this slide and Christoph's work, I think the journey has just begun to fixing it. So I think that it's going to take some time, and the legacy issue is probably what's going to make it take a long time. So we could fix these issues today, or not today, but we could fix these issues in a very, very short amount of time just by updating all the popular client-side JavaScript frameworks. But we have a lot of websites and web applications deployed already using old versions or other older frameworks that wouldn't have the benefit of those modern ideas like trusted types. So those are going to stick around for a long time because it's going to take a lot of work to rebuild them in the modern frameworks that have been made safe. And today we don't even have, a good level of safety in all of the modern JavaScript UI frameworks. So once we get to that stage, then we can start eradicating the bug class using modern frameworks. But it's going to take a long time for the long tail of those old applications to be phased out.
All right, one more question over here, and then I think we have to move on.
Thank you for the talk. What was your true positive ratio based on your tool that you developed? Were you able to...
true positive, that's quite easy. You just accept a lot of false positives and you get a very high true positive rate. So that's what I started with. I started with alerting on anything where the string showed up in a sink, which meant I had a good true positive rate, but it was drowning in false positives because almost all of the time the string is being quoted correctly, and single quotes, double quotes, angle brackets, all of that stuff is being converted into URL encoding when it ends up in the sink. So what I did was that I included what I call the filter string along with my tainted input, which contained these special characters. And then I could look for those at the sink and see, have they been encoded or not? And then I could use that to weed out the false positives. So I can only alert when I see unencoded characters at the sink. And that gives me a pretty good low false positive rate at the risk of then lowering also the true positive rate. Hope that gives some kind of idea of. But have a look at the code. It's on GitHub. You can look at all the crappy JavaScript code that I've written.
All right.
Thank you very much, guys.
Thank you.